Uh, Today, we're going to do more with magnetism. Our biggest new rule with magnetism is going to be Ampere's law. And there will be a quiz, which I'll make available at the end of class, but you don't have to do until, you don't need to finish until 11:59 if you want to take a break first. And it is on RC circuits. Any questions before we get going? All right. So just something to recap what we were doing last time and build off of. Let's, wait, that didn't work. Right, here we are. Right, so a current loop uh, so if we were looking down on it, it would look like this. Or slightly from the side, looks like this, just slightly above. And the magnetic field is going up through the hoop. So what will its torque and potential energy be? So see if you can work through it, figure it out. Useful. Torque. And our potential energy. So starting off with the torque, there would be none. So net force, there would be none because whatever net force this segment of wire gets, this segment of wire is going to get the opposite net force because the current's going in the opposite direction. So the force will be in the opposite direction as well. So there's not going to be a net force. Same with the top and the bottom, and the top right and the bottom left just all cancels out. So segments of the wire can experience a force, but the wire as a whole does not. And for the torque, there's not a net torque because right-hand rule, the area vector and magnetic moment of this hoop are already aligned with a magnetic field. So that cross product is going to be 0. But it does allow for a non-zero dot product. One, because there's just one loop, not coils. Our current is 0.5 amps. The area would be pi r squared. And the magnetic, to put a vector on that, I don't have a coordinate system yet. If I just went with the conventional coordinate system of y is up, then by the right hand rule, my magnetic moment is up. And the magnetic field would also be up. So y hat dot y hat is just 1, and this works out to be minus 0.0157 joules. So it's aligned, that's the lower energy alignment. If it was facing the other way, there would be a positive potential energy because there could be some torque that would flip it around to this orientation. Or if it was almost anti-aligned, there'd be torque to flip it around this one. Good on this.
So we had no torque because the rotation of that circle using the right-hand rule produces an up vector and the magnetic field's already going up.
Yes. So it's already in the position that the torque would, try and put it at. So this cross product between parallel vectors gives a 0.
Gotcha. Okay.
Right. And just for a quick one for right-hand rules. So electrons are coming at you. Oh no. So they're moving out towards you in that direction. So just make a sketch of what the magnetic field would be due to this beam of electrons coming out of this point. So if you right-hand rule that, it's important to remember that electrons are negative. So if the electrons are coming out, the actual current is going in. So right-hand rule, it's going to sweep around clockwise. And it is stronger closer to that beam of electrons and weaker farther away. An alternative way of looking at it is if you've got a negative particle, instead of using right-hand rule, you can use left-hand rule. So if they're coming out at you, the magnetic field would go clockwise around like that. So I want to take a bit of a closer look at the magnetic field that you would get from particles. So last class went over what wires could do. Nice and easy for long straight wires and more complicated for curved wires. But if it's just a particle, the magnitude of the magnetic field that you'd get from that has the same mu naught divided by 4 pi constant. So if we've got this charged particle moving along, the point that you're measuring the magnetic field has a distance from the charged particle that's moving, and there is some angle between them. So the maximal strength of magnetic field at any given distance would be when the particle is passing you. And if you're trying to detect incoming charged particles that are coming right at you, magnetic field would not be how you would do it. Magnetic field would be 0 directly ahead and directly behind it. To get to the actual magnetic field instead of just the magnitude, just turn it into a cross product. Or this cross product is what's giving us the sine phi term. So what if there were multiple charged particles? Well, for electric fields, if there are multiple charges that have an electric field, the electric field at any given point comes from the vector sum of the contributing electric fields. If you've got multiple forces, the net force comes from the vector sum of the forces pushing and pulling on an object. And if you have multiple magnetic fields contributing to the magnetic field in an area, you can just add up the things that are contributing. But importantly, just like with forces and electric fields, they need to be added like vectors. So we could take this particle and figure out what the magnetic field would be from two particles doing entirely different things over at this point over here. Sure, it's possible. Instead, I would like to look at what happens if we have that continuous stream of particles, like the beam of electrons or moving towards a current in a wire. So if there is a wire and we're just looking at a very, very small segment of it, so we're going to let the length of this become infinitesimal eventually and integrate over the length of it. So our total charge Q is going to be what we get when we integrate over all of the tiny segments of wire to get our total moving charge. Just like adding up every bit of charge in a stream of electrons, same idea. So our dq, or Q, capital Q, is going to be the total amount of charge in this wire or beam of charges moving, is going to be equal to the amount of charge over the whole thing. So this dq segment is just how much charge is in here, which is the product of the charge of every individual charged particle, which is going to be lowercase q, times how many charged particles are in this segment, which is just the density times the volume. Or the charge per particle times the density of free charged particles. And the volume can just be broken up into the cross-sectional area dl. dl is just our little length bit. So this can go into the magnetic field equation, the cross product equation above. Our new magnetic field element from that little bit constants stay the same. So the speed used, or the velocity used now, is just the drift velocity, how charges in this segment of wire move. And our charge is just the charge in that little bit. So this can be expanded. That dq can be this now. And I made the vector quantity the dl instead of the drift velocity, but it doesn't actually change anything because in a wire, they're going the direction that the wire goes. So it's the same direction. So changing which one gets the vectors change things. If we imagine positive particle moving along in that direction, the way it goes is the way the wire goes. Oh yeah, lowercase n, yes, density. Thank you for filling that in for me. So yeah, how many free charge particles we have. And things might flip around for a negative particle, but yeah, it all gets fixed when we turn it into I, because current is just the amount of charged particles flowing through per second, or charged particles density cross-sectional area. So integrating over all of it. Gets us back to the law of Biot-Savart. So it's not a really independent principle from how an individual particle would act. If you just add up each charged particle moving independently, giving a magnetic field in the box, integrate over it, all of it, you end up with the rule of Biot-Savart for getting the magnetic field from a current or currents.
So the R vector is from U to the stream of particles?
Uh,
Am I understanding that correct?
from the wire to you, or from where the measurement is being made.
Oh, okay, okay. Then I just had it backwards.
Yeah, I guess I should draw that one in because it has its uses. Yeah, so this is our charged particle. R goes from the particle or the bit of wire for the Biot-Savart law to the point that the magnetic field is being determined. So something that we've mostly looked past to up to this point, and we'll probably keep looking past for most of the class is, yes, moving charges make magnetic fields, but there's some inherent magnetic fields associated with some charged particles also. That electrons, probably called spin, that they seem to act as if they were spinning or moving in a tight circle and make a magnetic field that way. It's not a perfect picture of them, but there's thinking of a single point particle spinning doesn't make much sense, but it would have some magnetic field as if it had charge that was moving around. So single particles can have a north pole and a south pole. But we're going to ignore the other source of a magnetic field that a proton could have, which will be just fine for this. And just simple charged particle moving in a straight line. It's positive. And it's going fast. So at different points 1 nanometer from it, you'll find different magnetic fields. So what will be the greatest magnitude of magnetic field you could find and the least magnitude of magnetic field you could find 1 nanometer from this proton? So our magnetic field magnitude. Mu naught over 4 pi times the value of our charge, speed, times the sine of the angle between its velocity and where we're making our measurement. That is ugly enough to merit rewriting. Divided by the distance squared. So plugging in. Our charge is 1.6 approximately, times 10 to the minus 19 coulombs. Our velocity, 10 to the 7th meters per second. And our distance is 10 to the minus 9 meters. So a whole lot cancels out. But we end up with 0.16. Oh, Tesla times the sine of that angle. So the maximal value that this would be 0.16 Tesla. And the minimum magnitude that you'd get from this is 0. So directly ahead and directly behind, there would be no magnetic field from this particle, and 90 degrees off from that. So here and here, there would be a magnetic field of 0.16 Tesla. On this. Let us move to Ampere's law.
So that right there is what you meant when you said the field is strongest when you're passing it.
Yeah. Or when this angle phi here is 90 degrees.
So Professor, the maximum amount is 0.16, right?
Yes,
Okay.
Tesla.
Yes.
So Ampere's law is in some ways similar to Gauss's law. Definitely differences. It based on some different math, but a lot of concepts and similar. So for Gauss's law, we related how much charge was in any given area to how much field leaves. And there was a strict proportion to how much charge was contained to how much electric field or flux of electric field went along it. Ampere's law, if you have, instead of a closed surface, so something that's going to wall off a volume and enclose a volume, we're going to have a closed loop or a path that can carve out an area. So this isn't a current path, this is just an imaginary path for us to integrate over. I guess fitting the pattern, we can dotted line that path. So this could be in a plane, but it's just a loop that we're going to integrate over and do some math along. So that's what's doing our containing. And instead of relating to how much charge is inside of here, that relates to how much current passes through it. So looking to our magnetic field from a wire, the closer you were to a wire, the stronger the magnetic field. So if you look at the magnetic field close and the magnetic field farther away, it's stronger close, weaker far away, but integrating of the magnetic field along that inner path would give you the same integral as you would integrating along this outer path here. So this is Ampere's law in a nutshell. The integral of the magnetic field along a path. Is equal to mu naught, just the constant for magnetism, times the enclosed current. So for Gauss's law, you wouldn't count charges that are outside your bubble. And for Ampere's law, we don't count currents that don't pass through our loop. So it is, much like Gauss's law, much easier to use in simple systems that have a lot of symmetry. Doesn't mean it's wrong for more complicated cases. It's just harder to apply. So these are both nice circular loops. If you instead made your star-shaped loop around that wire, you would get the same integral, but nasty and ugly, but same answer. So any closed loop that encircles the same amount of current will get the same magnetic field integrated along the path of that loop. This is a rule that has a handedness to it. So the right-hand rule gives you what kind of current counts as positive. So all of the loops that I drew in, right-hand rule them, you get a vector going upwards. So currents that go up through the loop count as positive, and currents that go down through the loop would count as negative currents. So just to very clearly show how that works for a straight wire. Ampere's law. So our current is just constant I going upwards. B dot dl, B is what we're trying to find, but it should be constant along this circle because it's all the same distance from the wire. And there's no reason for it to be stronger on the left than it is on the right. So This is just going to turn into the magnetic field times the length that we're doing this integral over. Because it's constant. So our magnetic field is mu naught I over 2 pi r, which is exactly what you would, exactly what we had for the magnetic field from a long straight wire. It can be used in more complicated cases. So what if instead of treating our wire as just a line, we thought of it as a thick wire? So our Amperian loop could be entirely within the wire or outside of it. So if this wire has still a current I going upwards, a constant current density going upwards, then it becomes a question of how much of that current passes through the Amperian loop. So the current density would just be the total current over the total area. Or the total current over pi big R squared. So doing Ampere's law on this now, we need to be careful that we're not looking at all the current that exists in the world, but only the current that passes through. Because there's still the nice symmetry, we can just realize that our integral is the integral of a constant. But the enclosed amount of current is variable with little r. So I enclosed is going to be the current density times the area, pi r squared. Or the total current over pi r squared, big R squared, times pi little r squared. So this becomes Oops. So it depends on how far from the center the magnetic field is being measured. So in the exact center of this wire, there would be no magnetic field. And as little r got bigger and bigger and approached the edge of the wire, more and more current is enclosed in that loop. So the magnetic field gets stronger as it expands outwards until it reaches the edge, and then it's going to fall off because it's not enclosing more current, but it's still getting a larger and larger perimeter. So mathematically, same form as you'd get from Gauss's law for a cylinder of charge. Have a linear dependence on R until you hit the edge, and then an inverse dependence. So you could use this for current densities which were not constant, get a different relationship, but this is just one way to apply Ampere's law. So that looks like an obscene amount of current, but that's amps per square meter. So we have much less than a square meter worth of wire cross section. So the actual current is more manageable. Such wire. Three centimeters thick, that's its diameter. And what would the magnetic field be 1 centimeter from its center? So half a centimeter from the edge. And we just set I to be up if you want to be able to get a direction. So go for it, see if you can work it out. Use some Ampere's rules. So setting up an Amperian loop. Go like this. So the integral of the magnetic field along that path equal to mu naught times the current enclosed. That integral just turns into magnetic field times path length because you're always going in the direction of the magnetic field and it's unchanging just due to the symmetry of the system. And the enclosed current is going to be the current density times the area that has current flowing through it. So the fact that the wire is bigger doesn't really matter. The only current passing through our loop is what passes through the loop. So 1 power of the radius ends up canceling out. Because as it gets bigger, there's not only more current that passes through, but there's also a longer path to integrate over. This pi can cancel out. So the magnetic field strength would be 0.0377 Tesla, and the direction would be by right-hand rule, counterclockwise as viewed from above. So going around that way at 0.033, I'm sorry, 0.0377 Tesla. Good on applying this? Questions on Ampere's law? So there is a particular geometry that Ampere's law really helps with. And that is the solenoid. So just the coil O wires. Magnetic field of a current carrying slinky. The coil or on the cardboard tube that I did last time was like that. It works best if it is has a very large length in comparison to its radius. For this solution giving a nice, clean and accurate answer.
Sorry, Professor, I am interrupting you. For previous example, why didn't you use 3 centimeter or basically 1.5 centimeter for R?
An important question, and it's because Ampere's law cares about the charge, I'm sorry, the current, which is enclosed. So just like for Gauss's law, you would not count charge that's outside of your Gaussian bubble. For Ampere's law, you don't count current that passes outside of your Amperian loop.
So basically you use the same R for capital R and small r, 1 centimeter.
This time, yes, because the amount of charge contained was determined by the radius of the loop, not the radius of the wire.
Oh, so
If the
3,
wire would have been smaller, I would need to use the wire's radius to figure out how much charge passed through. But they were both determined by the size of the loop, so I used the same R in both cases.
so we just need to ignore the 3 centimeter thick straight wire, right? That's just confusion.
In that case, yeah, it
Oh,
is unnecessary information.
unnecessary.
Just like for Gauss's law, if you were trying to figure out the electric field in a charge of uniform, a sphere of uniform charge, and you wanted to know what the electric field was some radius little r away, you would make your Gaussian surface. And the surface area of the Gaussian surface is determined by little r. The volume of charge it contains is determined by little r. So how big the sphere is irrelevant so long as it's bigger than the area you're looking at.
Perfect. I got it. Thank you so much.
Good. So this would be difficult to try and sweat through with Biot-Savart. You could try and look at each turn as a circle, get the magnetic field from a circular loop, integrate over all of them. If you're on axis, so in the exact center of the solenoid, that would be of moderate difficulty. If you're not on the central axis, it's even harder. Ampere's law, not bad, much nicer. So for this solenoid, if we take the step of moving it from discrete loops to just estimating as it's close enough to look at as if they're almost continuous. It becomes actually a little more manageable. So we're going to take a cross-sectional slice of this solenoid. So just kind of cut it in half. And make an Amperian loop. It goes into it, through it, out of it. Or to look at a slice of something that's a little less messy. If we cut this and our current was flowing through this coil and going out and then in and then back around, and then when it got here, it's coming out towards us and back around and then into the screen, and then back around and out towards us. And just looking at that 2D cross-sectional element, then we're going to have a wire carrying it towards us, which loops around away towards away towards away towards. So these are all pretty much the same picture, just trying to look at it from different angles. And our Amperian loop be this rectangular path. So I'm just going to name the sides A, B, C, D. So Ampere's law. Around that closed loop, is equal to the magnetic field along the 4 lengths that make up that rectangle. So for a circle, if everything's the same, you just consider it one trip, but there are 4 steps to make this closed loop. So they ought all be looked at individually. For A and C, if we have a very, very, very long loop, and it just keeps going far in that direction and going far in that direction, then the step up, then the place where A goes in is pretty much the same as the place where C goes out. If we let ourselves assume that this is very, very long, the left square of a rectangle and the right square of a rectangle are not in fundamentally different places. B, the top end of the rectangle on the inside, is fundamentally different from D on the outside. But A and C, they're both just somewhere in the middle. And the magnetic field should be the same at A as it is at C, so it should cancel out. Also, if those were non-zero, then you'd have magnetic field that radiated outwards from it, and just have magnetic field just spreading out uniformly from some spot, which isn't what magnetic fields do. It makes loops, not radiating outwards. So A and C aren't going to contribute. D is also not going to contribute. And the argument for that is, what if there was a different Amperian loop? Like this. That Amperian loop does not contain any current. So does not contain any net current. The net flow through that loop is 0. So there should be no magnetic field along that path. Or the integral along that path needs to cancel out to 0. And if the vertical legs of that green rectangle cancel out to 0, then the top and bottom leg must also cancel out to 0. And the field for a solenoid, it's not actually always perfectly 0 on the outside, but it's close enough. So an arrangement like this, on the outside, things pretty much cancel out, and on the inside, they don't. So the only significant part contributing to the magnetic field integral along the loop of this rectangle is what's inside. The magnetic field is quite weak everywhere outside of the solenoid, except near the mouth, which we're not there. So this becomes magnetic field times length. And the amount of current that is contained, well, that's going to be how many wires pass through here, or how many loops we've enclosed, times the current per loop. Mu naught, and then just how many loops or how many turns pass through this rectangle times the current. So the magnetic field inside of that solenoid where lowercase n is how many turns per meter, or how many loops per unit length there is in this solenoid. So Ampere's law lets us exploit the geometry of this solenoid to get a not difficult answer for its magnetic field, instead of trying to use Biot-Savart and integrate over all of the turns, the entire surface of it would be rough. So solenoids are good tools for making strong magnetic fields, because you can just increase the number of turns per meter and get a strong magnetic field. They're also good tools for creating nearly uniform magnetic fields. If you want something that's close to steady, Ampere's rules would give the same answer here, where I chose to make that as if I made it farther in. So inside the solenoid, things are pretty much constant. That does fall apart near the openings. So to get a more complete picture of our solenoid magnetic field, I'm not going to draw all the winding curves, but just imagine it's winding around and around. The magnetic field is pretty straight and uniform on the inside, but it starts fanning out. The edges. And it ends up making a pretty similar magnetic field to a bar magnet, where outside of it, there's a fair magnetic field at the openings, but away from the poles, much, much less. And throughout the center, a pretty constant magnetic field near the middle. Good on our solenoid magnetic field. Let's see how using it goes. So this solenoid, it's 20 centimeters long. And it has a 2 centimeter radius, so a 4 centimeter diameter. And what is the magnitude of the magnetic field? Right there in the center, where the equation for calculating it works out quite well. Our length is well over our diameter. We're not near either opening, so the equation should hold well. And it doesn't have 800 loops total. It is 800 loops per meter. So it's important to realize the distinction between total loops and loops per unit length. So work it out. So magnetic field. Mu naught times turns per unit length times current. The solenoid's length and the solenoid's radius don't enter the equation. Our Tesla meters. Our turn density is just the 800 per meter. And our current is 0.2 amps. And this works out to be about 1 millitesla.
Professor,
Yes.
that 10 to the 7th, shouldn't it be 10 to negative 7th?
Oh, yeah, that minus sign should be there. Thank you. Yeah, the answer reflected it. The minus sign definitely was not there for you.
And I assume we're always gonna describe the loops per unit length in meters, considering it's meters and mu naught.
Yes, good catch.
Okay,
You could use mu naught in other units, but that way pain lies. So yeah, getting into the base units of loops per meter is definitely a good step. So yeah, if you had loops per centimeter or number of loops and length in centimeters, getting to loops per meter would be wise. So the units, meters, cancel meters. Amps
Professor,
cancel amps, and you're left with Tesla.
why we didn't use the length 20 centimeter? Because it's already mentioned that it's 20 centimeter.
The length doesn't have a significant impact on the magnetic field inside.
Okay.
The radius doesn't have a significant impact on the magnetic field inside. Which is kind of cool. You make it bigger, magnetic field stays the same strength. You make it smaller, magnetic field stays the same strength.
So we don't need to divide the 800 loops per L, which is 20 centimeters.
Correct. If there were 800 loops, you would need to divide by the length. But you were already given how many loops there are per meter.
But
So, yeah.
this is 800 loops in 1 meter, and we already have 20 centimeter of that, not 1 meter.
Yeah, so there aren't even 800 loops. We need to, yeah. There's not 800 loops, there's 800 loops per meter. So if you knew how many loops there were, you would divide that by the length to get how many loops per meter there are.
Okay, thanks.
Figuring out what to ignore is important. So you got a 2 times. It's very possible that there was a button clicking error when I did the math. I might have. Oh, did I not include the amps when I did my calculation? Oh, yeah, I made a button pushing error. Your answer is correct. It actually was 2 times 10 to the minus 4. I entered a symbol wrong. I dropped a multiplication sign. All right. A pretty cool thing that you can think of as using Ampere's law is a coaxial cable. So if you have, instead of a simple wire that is hollow, and on the inside, there's another wire. So they are coaxial, is in that they have the same central axis. So if you have something like this and you carry current in opposite directions on the inside and the outside, then if you make an Amperian loop around the whole thing, got I die. Like you could send power to a light bulb through the center, send current to it through the center, and back along the outside. And you need some insulation between the two. But the cool thing about that is this Amperian loop that goes around the cable has no current that passes through it. So this would not make a magnetic field. There would be some magnetic fields inside of it. So an Amperian loop there would encircle a net current. The one that went around the whole thing doesn't. So the current flowing through this wouldn't make magnetic fields that could interfere with other things, which is pretty neat.
I can imagine that might be helpful in hospitals and such.
Yeah, if you don't want, interference, if you've got something very, very sensitive, it's cool. It's not going to interfere with, because a current going through a wire making a magnetic field, nearby wires would feel that magnetic field, get forces on them. In most applications, that's not that big of a deal, but it's a cool way of just canceling it out.
Professor, would the currents have to be equal?
Yes, they would. If not, they would only partially cancel each other out. But if one path is the return of the other, then they would be equal. Just like if you have an electrical wire of, the positive and negative right next to each other feeding a device, those would mostly cancel out far away. But this would just do a better job of canceling out far away. So just, yeah, less magnetic interaction. Last thing for today. Magnets that are just magnets. So you've almost certainly used a magnet before that was not made by having a coil of wires and a constant current flowing through that coil of wires to make something that's a lot like a bar magnet. You just have a bar magnet. So on the atomic scale, some atoms have the magnetism of that individual atom mostly canceling out with itself. So it is an oversimplification to think of the electrons as making circular paths around it. Sometimes a useful oversimplification, not exactly true, but there is some angular momentum that on average an electron could be expected to have around a nucleus. And you could have one going one way, one going the other way. And the magnetism would cancel out. But if you have some things where those don't cancel out, often that will cancel out with a nearby atom. So if you have a current loop with a magnetic moment, and it's near another current loop with a magnetic moment in the opposite direction. If you're really close to them, these wouldn't perfectly cancel out. But if they're really close to each other and you're far away from both of them, the magnetic moment from these two loops would pretty much cancel out to zero. And the magnetic field that you experienced from them would be just about zero. However, in some materials, the magnetic moments of the individual atoms have a tendency to align. So this is where ferromagnetism comes from, where magnetic moments of individual atoms, which you can think of atoms as tiny current loops. It's not perfect, but it gets some of the good ideas across. So they add up. And if you have a material moving to bigger and bigger scales, the magnetic moments can align with their immediate neighbors. Sometimes, however, they align with their immediate neighbors, but they don't align over the entire material. So iron is likely to do something a lot like this, where different regions of the iron make different magnetic domains. So there's for complicated chemistry, energy reasons, they do a good job of lining up with their neighbors, but not necessarily getting the whole large solid chunk on the same page. So the magnetism of this thing on the whole may be pretty small, because things might not cancel out with their immediate neighbors, but the domains can, to a large degree, cancel each other out. If a strong magnetic field is applied to this, then you can change the magnetic domains. So atoms can be, switched to a new domain. So if there's a magnetic field applied to this whole thing, then this top left domain might grow. And that domain there might shrink. So the amount that is now aligned increases. If you apply something strong enough, you might just get all of it going the same way. If you really apply a strong magnetic field. So this is a so-called permanent magnet. If you took away the magnetic field, the alignment of the domains often persists, at least partially. So once something is magnetized, it usually, well, for some materials, different materials are different, holds on to that magnetism and is just a magnet now. If you applied a very strong magnetic field in the other direction, it could be flipped back. It also can be made chaotic again by hitting it really hard and just breaking up the order, or heating it makes the ordering break apart. But it can just be a magnet. So if you have a compass needle, you just get something that's magnetic, align it so it's all going the same way, and it will stay that way and be a magnet that you don't need a constant current wrapping around for it to work. Yeah, so the area that the magnetic field exits from is north, and the one where it enters is south. So this would have a north and south pole, absolutely. So the fridge magnet is not a fundamentally different thing than the solenoid magnet or just current going through a single wire magnet. So all magnetic fields caused by electric currents of some time, whether those are large scale occurrence or atomic scale motion of charges. It's just moving charges. I may do a little more on magnetic materials next time. I will also be moving into induction and inductors and how those work. But I would like to give you some time to take the quiz if you would like. So this can be a stopping point. Any questions before we're done?